Hello. Today we're going to discuss and show how to construct triangles, isosceles, equilateral, right triangles, using compass and straight edge, or circles and straight edge, no measurements, but how you can show, if you understand the properties of circles and perpendicular bisectors, that your triangles are exactly what you said they are, isosceles, equilateral, or right. So the first one's probably the easiest one. It's construct an isosceles triangle, and I'm using the inclusive definition, which means that it has to have at least two congruent sides. So an equilateral triangle would be a special case of an isosceles triangle. So it's the easiest one because we really only need our compass, which creates circles. Why is that? Well, what do we know about isosceles triangles? We need to have two congruent sides. If you think about a circle, every radii in a circle is congruent to all the other ones, and there are infinite of them because that is the definition of a circle, all the points equidistant from a center point. And a radius is a segment from the center to the outside of a circle, and all the radii in a circle are congruent, and I just need two of those to be my two congruent sides. So to construct a circle, it's very easy. You would take your compass tool. In our case, we're using geometric software. So I'm going to, obviously, there we go. I'm in my draw tool. So let's undo what I just did there. There we go. I want my circle tool, or my compass tool in this case. And I just want to put a point where the center is going to be, open my compass, my radius out to any distance at this point, it doesn't really matter, and make my circle. And now I get my straight edge, and I can put a point somewhere, anywhere. It doesn't really matter where, any other point on this circle. And I know that C to E is the same distance as C to D because they would be radii if I connect them. So let's connect them with a segment or a straight edge. If you were doing this with students, they'd be using a straight edge tool. So here I already know these two are congruent because I know my properties of circles and that all radii are congruent. So I have my two congruent sides. We could even, since I happen to be in my software, I could use the decorate tool and put my tick marks. If I were with students, this is something I highly recommend, that they always mark things that they have defined to be congruent or parallel or right angle, whatever it might be. It's important to identify those things. So now I have my two sides, and all I need is my third, and my third one would just be to connect these two points, E and D here, with another straight edge segment. And now I have, and I want to make sure that I turn that off, now I have an isosceles triangle. And it can be any isosceles triangle in this particular case because I can change the size, but because two of the sides are always the radii of the same circle, I always know this is isosceles. So that's the easiest construction, and it really is based on understanding about the radii in a circle being congruent. Let's scroll down to this next one, and before I forget, I was hiding my observations here, so this is sort of what we'd want students to understand, is that because it has infinitely many congruent radii, and they're all congruent, as long as I use any two of them and connect their points on the circle with another straight edge segment, then I have an isosceles triangle. Let's now go look at an equilateral triangle. So an equilateral makes this third side also have to be congruent, the same as the two radii. So we know a circle is involved. That gives us at least two. So let's start off with a circle using our compass tool. We're going to make a center point, open up our compass, construct a circle. So here's my circle. But now I know I can get two. How do I get the third one? Well, what if I had another circle that was exactly the same as this circle, so that its radius was the same as D to E or E to D? Well, I can use my compass tool again. Let's try that. So but this time I'm going to use the center. I don't want it to be the exact same circle. I want it to be a congruent circle, meaning it has the same radius. If I understand my properties, circles with the same radius are congruent because all the radii are congruent. So let's make another circle using our compass tools, but this time the center is the point that's on my already existing circle. And I'm going to go out to the center. So what do I already know? I know, and I'm just going to get my straight edge and connect these two. I know that DE is a radius. In fact, let's change the color of this one circle here so that we can see that they are two different circles. but they have the same radius. DE is a radius of the blue circle, but ED is a radius of the red circle. Since they are exactly the same, these two circles are congruent, which means any points that are on them or that are on both circles would be the same distance from both centers, would be radius. So if you notice, there's two intersecting points here, and let's actually construct those. And so students would do this. So notice that I get these two sets of points. So if I were to connect, again, straight edge, the center of circle E to this point that's on it, F, EF is the same as ED, they are radii. But then if I went into the circle D and connected D to F, that is also a radius, which is also congruent to DE. We can use our properties to know that if two objects are congruent to the same object, then they must be congruent to each other. But we also know that they're congruent circles. Therefore, all corresponding parts, all of these are radii, are going to be congruent. So I now know that all three of these are congruent. So I could put tick marks on it. Now, did I have to use point F? No, I could have actually used point G. I actually could make another congruent segment here. Congruent triangle here, equilateral triangle. So basically, you're using two circles for equilateral so that you end up with two congruent circles, and you're using the radii of both to help you make your equilateral triangle. And so if we look at our observations, that's what that's all about, is the circles are congruent, so the radii are congruent, and you can connect all the radii and make an equilateral triangle. The last one's a little trickier, a right triangle, so I need to have a perpendicular in here. So here comes my understanding of a perpendicular bisector, and also the idea that a segment is a part of a line. You're only looking at part of a line when you're looking at a segment, and so that if you have a segment but you need something more, if you need a little bit more, you could actually add in the auxiliary line, the rest of the line, in case you need it. And that's what we're going to need in this particular construction. So I'm asked to make a right triangle, so I need one side. So let's just make a side. And my perpendicular needs to either go through point A or through point B. It doesn't matter which one, but I need a perpendicular through this point. And in order to do that, I need to have the rest of the line a little bit. So I'm going to get my straight edge, which down here in my tools is a line. And I'm going to change the color just so that it stands out. I'm going to make it yellow. And I'm going to make it dotted so that it looks different from my original segment. So remember, this segment is really just a piece of a line, and we don't see the rest of the line. I'm going to basically put the rest of the line on. And so to do that, I've got my straight edge tool, and I'm just going to basically extend the line that AB is sitting on. So you can see AB is my original segment, and I've basically showing the rest of the line. Why do I care about that? Well, I need to now think about perpendiculars, and the easiest construction for a perpendicular, you always have to go back to a perpendicular bisector, because you can use circles and congruent radii to help you with that. So let's say we decide we're going to put the perpendicular through B. So I'm going to get my compass tool, and I'm going to make B the center of a circle. And again, it doesn't matter how big the circle is. What I want is that it intersects my line. So I'm going to connect it there. Oh, let's make our circle not yellow so that it stands out a little bit more. Let's make it green. So there's my circle. So notice it intersects the extended line here, and it also intersects the original segment. So let's make that intersection point. And so now you'll see I have another segment made of D and E, but I know that the distance B to D and B to E is congruent, right? They are both radii of this circle I just drew. So now I can do the construction for a perpendicular bisector, because if I can create the line here where D and E, all the points on it are equidistant, then I know that I have a perpendicular bisector. So here's where my compass tool comes in handy again. So let's change the color one more time. Let's make it red. And I'm going to now make, this is how you do a perpendicular bisector, which at this point students have already done. But I'm going to use the points D and E as my radius for two different circles. So I'm going to open my compass with a center at D, open, oops, I need to get my compass tool. Center at D and open to E, right? And so now I know that every point on this red circle is equidistant from D, including E. And now let's make another circle with center at E, open to D. And I know these two red circles are congruent. Again, it's that understanding that since they had the same radius, all the points on each of them are the same distance, they have the same radius. So these 2 points where they're intersecting, let's make that intersection, are equidistant from both D and E, which is the definition of a perpendicular bisector. All the points on a line that are equidistant from 2 endpoints of a segment are on its perpendicular bisector. So knowing that F and G are on the perpendicular bisector, I can now get my straight edge tool, and let's change color one more time, and connect them with my straight edge. And I know this is the perpendicular bisector, and maybe we don't want it to be dotted. There we go. I know it's the perpendicular bisector, and it's perpendicular to B because we made B be that midpoint of the original circle. So now I know that this line here is perpendicular to the original segment AB and at point B. So now, have I made my triangle yet? No. My triangle is now just going to be making sure I have a point on this. So let's get the polygon tool. Students would use, a regular, just a point on their line somewhere. As long as I put the point somewhere on this perpendicular, I know that it will remain perpendicular at B to AB. And so now I'm going to connect the 3 vertices, so A to B to H. And now I have a right triangle because I constructed this line HG to be perpendicular, and so I can make this be many different triangles, but I know that they're always perpendicular, that it's always a right triangle. And if you were actually, wanting to see just the triangle, you would hide all of the constructs behind it, but I want to make sure you understand that it's based on the understanding of both circles, radii being congruent, understanding a perpendicular bisector equidistant from segments, and so why we can add in this auxiliary line and help us get to a segment where that point we want the perpendicular to go through is a midpoint. All of these things are prior knowledge that students would need to do these constructions.